we investigated whether we could use a deep neural network and/or an autoencoder to demodulate digital radio signals using only a visual representation of the received, noisy version of the transmitted signal. We chose a vocabulary of 20 sequences, 4 symbols each, from a common digital format, 16 QAM, or quadrature amplitude modulation. Injecting the noisy image of voltage over time, we classified into the 20 corresponding categories. QAM signals are represented as a constellation, a rectangular array of points on a grid. The job of a receiver is to assign each received, noisy point in the plane to the constellation point it was intended for upon transmission. Noise misaligns the received points from the original grid. In the time domain, the signals are pieces of sine waves with controlled amplitude and phase. In the time domain, noise shows up as jagged distortion that randomly varies the voltage at each time point. We created a vocabulary of 20 different sequences of 4 QAM points to work with. To help with logistics, we assigned letters to QAM points and transmitted 20 different 4-letter words such as cart, pike, and time. We generated multiple copies of each word with various noise levels for input to our neural network and classified into our 20-word vocabulary. For the autoencoder, we used 3 different words and trained the network to create clean versions of the noisy input signals. For the convolutional neural network, we leveraged the VGG16 architecture with transfer learning. The CNN input format is 243 by 462 pixel grayscale images with various levels of noise. The CNN's output is classification of the images into one of 20 classes. Our CNN loss function is cross-entropy. The CNN is implemented in Keras with a TensorFlow backend. Images are shuffled and we rescaled the pixel values to a range of 0 to 1. Due to the characteristics of our signal, for example, a flipped signal may be the exact trace of another valid signal, we did not flip, shift, rotate, or zoom the image. Image datasets are split to 60% training, 25% validation, and 15% test. We define signal to noise, or SN, as the ratio of signal power to noise power for each individual sample. For experiments, we first tried SN levels from 2 to 10,000, at which time we found the accuracy to be very high after just 2 training epochs. Analyzing the situation, we believe it is probably caused by a situation where we have some cases of such low noise that even distinct noisy signals at this low noise level are so similar to each other that these training set samples are not meaningfully different from some test set samples. An analogy may drive the point home. If we were training a neural network with pictures of 20 different cats and used images differing only in the degree of blurring, then if some of the training and test images had blur level set to almost 0, we would have essentially the same image in the training and test set. For this reason, we limited the noise to much higher levels, SN of 2 to 50. The slower training indicates this is likely a more valid situation. We experimented with different hyperparameters, including batch size, dropout rate, learning rate, atom optimization decay rate, number of layers, and number of neurons in each layer. Our final architecture is VGG16 without its originally fully connected layers, replacing them with 6 new fully connected layers of size 1024, 256, 126, 64, 32, and 20. Our final hyperparameters are batch size 2, dropout rate 0.001, learning rate 10 to the minus 4th, atom optimization decay rate 10 to the minus 6th. We are getting 96% training accuracy and 93% validation accuracy. Confusion matrix for the test set is shown in the poster. For the autoencoder, we used the Keras standard autoencoder architecture with modifications. The encoder network comprises an input layer and 2 two-dimensional convolutional layers, followed by a flattened layer and a dense latent vector layer where the compression happens. The encoder network feeds into the decoder network. The decoder network comprises an input layer, a dense layer, a flattened layer, and 3 two-dimensional convolutional layers. Our goal is to reconstruct 3 different classes with various SN levels ranging from 2 to 200. We used 180 training images with 60 images per class and 45 test images with 15 images per class. On the autoencoder, after experimentation with hyperparameter tuning, we settled on a stride of 2 and a kernel size of 3. We found this allows for relatively fast training time while still capturing the key features for compression. We experimented with running 20, 50, 75, and 100 epochs. The network converged after about 75 epochs with validation error of 0.0011. The final outcome? The autoencoder did a good job of removing the noise and reconstructing the clean image for all three classes.